Hello and welcome back to another applied calculus lesson. In this lecture we bounce back into chapter 5 where we're going to revisit the definite integral and try to investigate its units in a little bit more depth. This will be useful as far as trying to relate the definite integral to some real-world models and things like that. So to begin with, we're going to recall that given a continuous function, f of t, defined on some interval, say a to b, the definite integral, the integral from a to b of f of t dt, is returning signed area under the curve. Now you might recall how we defined this in the beginning. We did it by approximating this area through use of rectangles. We saw that this f of t sitting inside of this integral, this was representing the height of the rectangles in question, and then the dt was somehow representing the uniform width of the rectangles that we approximated the area with. Of course, the f of t is some sort of an output of a function. The dt is a change in input, so the input and the output of this function f are going to have units if you're dealing with a real-world problem. So it turns out then that if we want to compute this integral, which is going to be the area of these rectangles, that area of course is computed by multiplying the height by the width, and so the units of this area, the unit of measurement for this definite integral, will turn out to be the product of the units for f and the units for the input x. So, for example, if both x and f of x are both given the same units, for example, say centimeters, then their product is, of course, centimeters squared, meaning that the units for this definite integral is given as centimeters squared. But of course, this shouldn't be too foreign to us because this definite integral was computing signed area under the curve. Of course, area is given by the units, say centimeters squared. So that sort of makes sense. However, the definite integral can do more than just compute the areas, because depending on what the function f here is modeling itself, whatever the product of units are between f and t might cancel and give something more interesting. For example, when we very first started our investigation in chapter 5 with the integral, we started with this idea that f was modeling velocity. And the units of velocity, this rate of change of position, is of course given as meters per second. The input t is of course given in seconds, so therefore the product, that is, the units for the integral of f of t dt, in the case that f here is velocity, turns out to be meters per second times seconds. The seconds cancel, and therefore this integral is returning just meters, as opposed to some sort of an area, like in the previous example. If in fact our function itself was modeling a rate, then the units of the area under the curve turns out to just be whatever the object is that the function was taking the rate of, in this case meters. But things can again get more interesting, all dependent on what this function inside of the integral is actually trying to model. For example, here, c of t can be a function here that represents the cost per day to heat your home, where that cost is being given as a rate, and that rate is dollars per day. Of course, t here is time, and that's going to be measured in days. T equals 0 is corresponding to the beginning of the year in 2014, and so the definite integral, for example, from 0 to 90 of c of t, it might be something of interest. So we'll ask ourselves, A, what are the units of this integral, and what is this particular definite integral actually computing for us? Well, the units, as we've described them, are what? They're going to be the units for the function c, which, notice that those units are given in dollars per day, so it's going to be dollars per day multiplied by the units for t, and the units for t, of course, is time measured in days, So that's going to be multiplied by the units for t days. And just like we saw in a previous example here, when the function in question is representing some sort of a rate, the units for the integral then cancel in some way, and you're left with just what it is that this function is taking the rate of, which in this case is the rate of dollars. So the units for this integral are going to be dollars, and in particular, the integral from 0 to 90 of c of t dt is representing the cost in dollars, because we have to be careful about our units. The cost in dollars to heat your house when? Well, if 0 is corresponding to the beginning of the year in 2014, 90 is going to correspond to 90 days into 2014. So this definite integral is actually computing the cost in dollars, not just to heat your house whenever you want, but to heat your house for the first 90 days of the year 2014. So this is another example in order to get us a little bit more comfortable with how the units of a definite integral come to be. Now, another thing we talked about in the beginning of chapter 5, is we introduced the notion of the definite integral, and we talked about how it's actually representing total change. That is, we said the following. We said that the definite integral from a to b, if f is representing a rate of change, then this integral is representing total change in the quantity between a and b. This is eerily reminiscent of the example we just did here. Here, c of t was representing a rate, and therefore this definite integral was representing a total change in cost for the first 90 days. That's exactly what we have here. We introduced this in a previous lecture because it allowed us to then define the fundamental theorem of calculus, which we used in chapter 6 in order to help aid us in actually computing antiderivatives and questions along those lines. Revisiting this notion of total change, though, we can now answer a few cool applied real-world problems. For example, here we have that a bacteria colony initially has a population of 14 million bacteria. We are going to suppose that t hours later, the population is growing with a rate given by this function, 2 to the t, given in millions of bacteria per hour. So if this function is given in terms of a rate, we know immediately that the integral of this function is returning total change. So the first question is, let's write down the definite integral that represents the total change in the bacteria population for the first 2 hours. So the key thing to note here is that since f here, f of t equals 2 to the t, is a rate of change in population, that's the key observation. That means that we can use this definition of total change. So once we know and make that observation, then we can observe that the change in population from t equals 0 to t equals 2 is therefore equal to the definite integral from 0 to 2 to the t dt. Now, you may still want to ask yourself, how do I actually compute that integral? And that is a really, really good question. Last lecture, when we were still in chapter 6, we helped work toward understanding how to compute antiderivatives, and in particular, we did put together a notion of how to compute indefinite integrals. What we're going to learn in the next lesson, which is going to be section 6.3, is how to use that information for indefinite integrals and the fundamental theorem of calculus to help combine those ideas to provide a streamlined way to compute exactly these types of definite integrals. But for now, when we're here in Chapter 5, we're simply going to be content writing down the integral, and then next lesson we're going to learn how to actually compute that value. That said, a question we might ask as a follow-up to this one is, okay, well, set up an expression involving integrals that in particular doesn't necessarily give the change in population, but gives the actual population at time t equals 2. This is where interpreting total change as a sort of fundamental theorem of calculus turns out to be super important, because the total change in population is actually just going to be the population at 2 hours in minus the population at 0 hours in. So what that means mathematically is the following. By the above line, which is what we have here, what we have is that the population when t equals 2, whatever that population is, if we subtract off the initial population when t equals 0, this quantity right here is literally the change in population, and therefore we know that this difference is equal to the definite integral from 0 to 2 of 2 to the t dt. So we can reorganize this expression and rewrite this to solve for the desired quantity, which is the population at time t equals 2. That's going to be this first bit, meaning that the population when t equals 2, this is the quantity we're interested in, turns out to be equal to the definite integral from 0 to 2 of 2 to the t dt plus the population when t equals 0. But, of course, we know what this quantity is. That's the initial population of the colony. If we come back to the beginning of the question, it tells us that the bacterial colony initially has a population of 14 million bacteria. So what that means is that the answer to this question is the integral from 0 to 2 to the t dt, plus magic 14. And this right here is exactly an expression involving an integral that returns the population 2 hours into the colony growth. Now, if you wanted to frame all of this in terms of antiderivatives, of course, these quantities, this population and this population, would be rewritten as something like capital F of 2 minus capital F of 0. You'd probably end up writing it this way. You'd say f of 2 minus capital F of 0 is equal to the integral from 0 to 2 of 2 to the t dt. And that's a perfectly fine route to take by using the fundamental theorem of calculus, but unfortunately that's something that we're not going to sort of go through in excruciating detail until next lesson in section 6.3. So for now, we're going to sort of resign ourselves to simply interpreting the quantities in terms of total change for this section, because we're focusing on the units and things like that as opposed to how to compute the final quantity.